Hi, my name is Jonas. I am from Copenhagen, Denmark. I'm currently in LA to study at UCLA Extension. I've had the great opportunity to participate in this CleanTech Connect project, be paired up with my mentor Chris Fulton, and it's been a truly amazing experience so far. So the objective we were given was how to get to 100% renewable energy. But before I dive into that, I would like to talk a little bit about what renewable energy is. So the US Energy Information Administration defined renewable energy as energy from sources that are naturally replenishing but flow limited. They're virtually inexhaustible in duration but limited in the amount of energy that is available per unit of time, which is very important. And more specifically, this counts as wind, solar, biomass, geothermal, hydro, and oceanic. So where are we today in getting to 100% renewable energy? Well, in the US in 2017, 11% of the energy consumption came from renewable energies, where petroleum and natural gas are still the largest contributors. If we look at the worldwide perspective, we can see that renewable energies have now surpassed natural gas, but is still coming a little bit short of coal, but is it definitely going in the right direction. On a more country by country scale, we can see that Norway is leading with 97.9% of renewable energy, which is largely coming from water powered renewable energies. So, how do we get to 100% renewable energy? Well, I've decided to divide it in three areas. One is eliminating carbon from the electricity sector. Number two is moving other sectors to electric ones. But if we eliminating carbon from the electricity sector, it's obviously to make it all coming from renewable energies. And then the other important part is to move other sectors over to be electrified so they can take advantage of that as well. And number three is to create a stable grid that will avoid blackouts, and in that way deliver the stable backbone of the whole system. So I've decided to focus on that because I believe that if you create a stable grid, it's really important to get that before moving everything over to the grid. So if we look at what blackouts is and why they are such a big problem, blackout is defined as a total loss of power to an area and is often caused by faulty equipment, accidents, or natural disasters. It's estimated that from 2000 to 2004 there was an average of 44 reported grid outages per year in the US, and from 2010 to 2013 there was an average of 200 reported grid outages. So that's an increase in 6 times from 2000 to 2013. Furthermore, it's estimated that the annual cost in the US of power outages is about $150 billion. So it's a pretty big problem in that sense. So for this presentation, I would like to go through three key components. One is the decentralized microgrid, number two is stable and viable storage solution, and number three is blockchain-based technology. And if we look at the centralized grid today, we can see that it's power that is generated by a central power plant. It is then stepped up in high voltages of a couple of thousand volts to be transported over long distances, then stepped down again, and then finally arriving in the houses of about 120 volts in the US and about 220 volts in Europe. And if we compare the centralized and the decentralized grid, you can see that the centralized grid has a few disadvantages, one of them being that the long distances and the amount of equipment in a centralized grid will increase the risk of breakdowns because equipment can get faulty, the weather can ruin power lines and other parts of the system, and because you're transporting energy over those long distances and in high voltage, there's a big loss in transmission of around 7%, which is mostly due to heat being generated. In the decentralized grid, we have a smaller risk of breakdown because there is a smaller grid and with smaller distances, and when a breakdown could happen, it will affect fewer people because the grid is not connected to the other grids in that sense. We have almost no loss in transmission, just under 1%, again because these voltages is not stepped up to those high voltages, so not a lot of heat is getting lost. There's higher transparency for the consumers because they can better understand and see exactly what the power is coming from and how it works. And finally, and very importantly, there's a low risk of attacks because with a centralized grid and as the grids are getting more digital, they pose a potential risk of getting attacked as part of a terrorist attack or hacker attack. But because they're decentralized, it's more difficult to attack the whole grid at once. It's estimated by a professor of energy at the University of Texas in Austin that will cost around $4.8 trillion to maintain the current grid in the US. This is simply just by maintaining every part of the grid and not necessarily by making it better or making it into something else. For the creation of microgrids, storage is a really important part. And as I mentioned in the beginning of defining renewable energy, you can see that they're flow limited and they're limited in the amount of energy available per time. So that means that when the sun is not shining, when the wind is not blowing, you cannot have as much energy. So it's about finding a way to store the energy in an effective way. These are just 4 examples of storage being used. There are obviously more sources out there, but these are the ones that I found most appropriate for a small microgrid scale. The first one is lithium-ion batteries, which is the most common used at the moment, mainly because it has a really high efficiency of about 90%. It's fairly cheap and a lot of research and development is being put into it. The disadvantage is that it's a scarce resource, so it means that there's a limited amount of lithium out there, so it's not a viable solution in the long term. Hydrogen is a good bet on a long-term solution in a greater scale, but it requires more development as the moment it's just under 40% of efficiency. If we move to the smart microgrid, you can see that the microgrid is an interdependent grid that has its own power sources, its own storage, and is connected to the main grid, and it's also connected to other grids. It will deliver power to smart homes and non-smart homes at the same time. And the smart part of the grid means that when it's communicating with non-smart homes, it can only see the amount of power they're using and when they're using it. They cannot see exactly what the power is being used for. If it's a smart home, the smart grid can connect and communicate with each individual device in the smart home and make it way better in the sense that it can make information-based decision, and it can see exactly when the power is being used for what device and for what duration of time. And in this area, I feel that Inspire will have a good opportunity to connect what they're doing with a smart microgrid to be able to provide a way better solution for the energy consumption. So why is it a smart grid? Well, the main reason is that it's connected. So it's not only connected to the individual units in the grid, it's also connected to the other smart grids and to the main grid. So this means that it can communicate between each grid, and it can also communicate with the main grid in sharing information and also in sharing power. It has a lot of incentive for the users because, especially if it's a smart home it's communicating with, it can provide deeper insight to how the power is being used and what the individual users can do to create a more sustainable energy consumption. And it's actually not necessarily about saving energy. It's more about demand response. So it's about using the energy when the energy is there. So if the sun is shining, the wind is blowing, you have a better opportunity of using energy and filling the storage. And if the smart grid will use machine learning, it could actually do weather predictions by learning about the different weather predictions coming in the next couple of periods, and using that information to compare it to the estimated average energy consumption by the grid to figure out whether or not there will be a surplus of energy in the grid, or if there will be a need to buy energy from the main grid or from neighboring grids. This brings the blockchain part into it, because blockchain is absolutely a buzzword of 2018. It's not all areas where blockchain is needed, but I do think that it has a role to play in a microgrid. The reason for that is that it's a peer-to-peer network. So that means that the system in the grid is not stored in one single place, but it's distributed over all the units in the grid. So this means that it's more secure, it's more fast, and it's cheap, and it has a higher transparency for the users in that you can actually see the grid, the system behind the grid, and all the transaction that's part of it. It could feature self-executing smart contracts, what that means is that it's contract that will be executed when a certain thing happens. And this can be used for paying the utility bills in the grid automatically without the need of human interference. It can also be used to facilitate transactions between each individual grid in selling or buying excess power. So the The smart contract will simply send the power and facilitate the transaction of either sending or receiving money, which again will provide another incentive for the users to save energy, because they know that they can sell excess energy to other grids and then have a lower utility bill. And lastly is the safety part. Because it's a decentralized system, it means that it's virtually impossible to hack, because the blockchain is part of all the units in the system. And that is really important, as I mentioned in the beginning about potential attacks, that the grid itself it's connected to the main grid, but it's not dependent on it, and it's also safe in the way that the blockchain is distributed. There's a quote from Inside Energy that I thought was appropriate in this area, and it says that if all smart meters accomplished is cutting costs for utilities and telling us when the power is out, then maybe the smart grid isn't as smart after all. So that means that it will be required for the smart grid to actually do smart things like self-executing contracts and automated workflows to actually work together with the units in the grid in order to be truly smart. So what will it cost to do a transition to smart grid? It's estimated that the whole cost in the US over the next 10 to 15 years will be up to $1 trillion. But it's also estimated that doing so will provide savings of up to $3 trillion in the same period. So there's also an economic incentive to transition into complete smart grids over the US. If we look at the road ahead, it's important that the government and the lawmakers will pave the way in pushing the current grid and the current energy providers to make improvements to the grid and to make improvements that will help facilitate the creation of smart microgrids. It's also important that we work together with the existing energy providers. Instead of looking at them as competitors, we could look at them as collaborators by collaborating with the main grid and the microgrids, and also collaborating with them to create smart microgrids. And lastly, it will be important that money will be poured into startups that are working in clean tech areas as an incentive to innovate and push innovation in the smart grid areas. If we look at the in the capital in the clean tech, you can see that venture capital only gives about 7.6% of all venture capital deals are put into clean tech companies, and out of those 7.6%, only 13% is actually put into the early stage companies. So this tells us that there's not it's not really a welcoming area for clean tech, because there's not a lot of money being poured into it, and for the money that is being poured into it is being poured into other parts of the development. So it means that the early stage companies will not have a great chance of succeeding, which in turn will break the innovation processes to help create the smart grids. So it's really important that the venture capitalists will start pouring more money into the in the early stage clean tech companies, and it's also important that the lawmakers will make it will provide incentives for the venture capitalists to do so. So in this presentation, I've gone over my solution of moving closer to 100% renewable energy by creating micro smart grids that will help avoid blackouts by providing a stable energy for the users. It will also provide a more transparent energy system, and it will have a smart factor that will actually incentivize users to use less energy and to use it in the right time, and also to sell and buy energy from each other in a completely self-sufficient system. Thank you very much for letting me be a part of this CleanTech mentorship program. It's really been an amazing experience, and I really enjoyed working with Chris in getting to this. And it's definitely been a challenge to grasp this whole area of getting to 100% renewable energy, because it's a really, really big subject. So I definitely faced some challenges in getting into to the more specific parts of it. So it's been a great learning experience, and I really hope to be able to work together with Inspire again at some point. Thank you so much.